looking into what are dynamic analysis. In a structure, last class we have modeled a structure for 2 BHK. That is, let me show the plan, and the plan consists of this is your plan. It consists of 2 BHK in ground floor and one kitchen, a dining, living room and a sit out area. These are the components of your buildings. We have designed the structure and modeling is over. Yesterday we have discussed dead load, live load. So these are called static analysis. Right now we will be discussing dynamic analysis. First thing, in dynamic analysis, before going into that, we have discussed wind analysis yesterday. It is a part of dynamic analysis, and earthquake is the second one. When considering the earthquake, the code suggests that the following assumptions. Earthquake motions are complex. Before starting anything, the code suggests that earthquake ground motions are complex, and since we have predicted more number of earthquakes, but the intensity, the magnitude cannot be predicted accurately. Why? Because due to its complex in nature, still it is under research. Hence, the assumption first word starts that earthquake motions are complex. Here you can see a building which is shaking due to long wave. So these are all not short waves. Due to short waves, the buildings will not deflect more, especially the tall story structures. Okay, now in tall story structures, due to long waves, the structures may vibrate in this manner. They consist of several frequencies. So for each and every floor, we will be having the fundamental natural frequency, and number of floors. According to the number of floors, you will be having number of mode shapes. The fundamental natural period for each and every floor, we have to find it. In analysis, we will be making the each and every floor into a diaphragm. Okay, they consist of several frequencies and they last for a small duration only. And amplitude also reduces. Earthquake doesn't takes long for 1 minute or 2 minutes like that. Therefore, the resonance cannot occur. So there is a concept of resonance. The structure will get highly oscillated due to the concept of resonance. So generally, due to earthquake, the resonance will not occur, and the code says that due to long waves and the tall structure founded on deep soft soils might have some resonance like deflection. So you can see the deflection here. These are all tall structures, and due to the long distance waves, this structure seems to be wobbling here and there. This is called drift. Technically, it is called a drift. Earthquake is not likely to occur simultaneously with high wind, maximum flood or maximum sea wave. When you are analyzing and design for earthquake resistant structure, you don't need to consider wind analysis, or if you are going for wind analysis, you don't need to make earthquake analysis. So either one you can do it. The B part of assumption says that earthquake and wind both does not act simultaneously. Okay, maximum flood or maximum sea wave. When you are constructing a seashore structure, you can consider any one of the phenomena and take the maximum load. Okay, there are two types of modulus of elasticity. One is static modulus of elasticity and second one is dynamic modulus of elasticity. So in research, you would have seen that, and elastic modulus for static, that is Young's modulus for static, is enough to design a structure. You can follow IS 456 for reinforced concrete structure, IS 800 for steel structure. Let us go to next thing. What are the different types of dynamic analysis which are available? They are, first one is equivalent static method, which we are going to discuss now. And in dynamic analysis method, equivalent static method is a part of static analysis. Even though the earthquake wave is dynamic, the dynamic load is considered into a static load. They perform the analysis. They are called equivalent static method. in dynamic analysis method, you have spectrum method, time history analysis method, and model time history method. So these three methods are available in dynamic analysis. Which technique to use for your structure? Their structure height might be less than 10 meter. You can use equivalent static method analysis and you can proceed with the rest of the thing. If your structure is a tall structure and if you have number of irregularities in structure, and what about your geological features? So according to the geological features, you can decide either you can go for response spectrum or time history. So this depends on the factors. Okay, let me discuss each and every one. Minimum design lateral force. Buildings and portions there shall be designed and constructed to resist at least the effects of design of lateral force as per the specific phenomena. The recent revision in earthquake resistant structure IS 1893 suggests that all the buildings which are constructed in India should have at least the minimum earthquake resistant force. That is, there are 4 zones in India. If you are constructing any house, it should be having minimum earthquake resistant force from zone 2 to zone 5. And in that zone, you have to consider the earthquake load and proceed your design. So no structure has to be designed without seismic consideration. Okay. Now, what do you mean by equivalent static method? Before we are looking into the analysis, you should know certain parameters in order to go to the hands-on training in Etabs. Okay. When to go for equivalent static method is the code suggests that this method shall be applicable for regular buildings with less than 15 meter in seismic zone 2. If your building is in Bangalore, Bangalore comes under seismic zone 2. And if you are constructing 15 meter height of a structure, then you can use equivalent static method. If you are having in different zone, this is not applicable. If you are located in zone 3, if your structure is 15 meter height, the code does not suggest that to go for equivalent static method, you can go for the next level called response spectrum method. Okay, this method should be used only for this structure, and you have to find the base shear, that is VB. Earthquake waves are being transmitted from the ground, from the focal point wherever the earthquake wave starts. From that point to each and every building, it starts to travel in the geological mass, and throughout the mass, when it transfers into a wave form, and when the wave hit the structure experiences the vibration. When your structure is shaking, what happens? There will be a shear. So this is called a base shear, VB, to be computed for a building as a whole. So you have to consider, you have to first find the base shear, that is design base shear, and you have to complete for the building as a whole. Okay. Now the VB shall be distributed to various floors at corresponding center of mass. If you are having 3 number of floors in your building, then you have to consider 3 number of shear force, and it has to be transferred to each and every floor. Totally what it happens, at the top floor you will be having 0 base shear, and at rest of the floors you will be having reduced base shear, and at your plinth level of your area you will be having the maximum base shear. You can find the phenomena here. Each and every floor has to be made as the floor diaphragm. Now you have to find VB, that is base shear. Any principal direction, VB can be found out by VB equal to AH into W. What do you mean by AH? Acceleration, that is horizontal acceleration. W is the self weight. Okay. Now how to find the acceleration, that is AH into W? Let us know that the AH can be found out by making our model to input the equivalent static load. Okay. This method may be used for analyzing a regular structure. If you are having too much of eccentricity, it might be mass eccentricity, geometrical eccentricity, or stiffness eccentricity, then you cannot use equivalent static method. This can be applied for regular structures with natural period TA less than 0.4 s. That is, TA is time period should be less than 0.4 s in dynamic phenomena. So in this point, it has been straight away given that if your structure is 15-meter height in seismic zone 2, you can use that. But here it has been mentioned that your fundamental natural period, fundamental natural frequency should be less than 0.4 seconds in order to apply this method. Okay. Now, how to find the fundamental natural frequency of a building without even analyzing. So, the code 7.6.2 gives a guideline that bare moment resisting frame without any masonry infills, whatever we are doing now. So, this is our model. So, currently you can look this model. Yes, this is our model. You don't have any infill walls. So, these are all called claddings. So, we have just added the claddings. So, we have not included the masonry wall. What we have done is we have just given the dead load for the masonry wall and we have taken only the load for that. This kind of structure you can use response spectrum method, equivalent static load method. TA, what is that? TA is fundamental natural frequency of the building 0.075 h power 0.75 for RC moment resting frame building, and for RC steel composite building you can use this formula, and for steel moment resting building you can use 0.805 power 0.75. Here you can see that buildings with RC structural wall, TA is taken as 0.075 h power 0.75 divided by root of AW. So, this is the formula when you are using infilled walls. If your walls is filled with the brickwork, what you can do is this formula can be used to find the fundamental natural frequency. Now, why before doing the analysis in Etabs, you have to check this, because your structure fundamental natural frequency has to be found here. Okay. Now, let us take our case as ordinary moment resisting frame. Okay. If this is the case, you can take it as, so let us calculate here. Your structure height is 0.075 h. The height of the structure here, this is 3 meter. From the first floor height is 3 meter and second floor height is also 3 meter. So, totally you have 6 meter height. Power is 0.075 into yes, your fundamental natural frequency of the building is 0.287, that is 0.29, we can take it as 0.29. Okay. The code suggests that your structure is lesser than 0.4 seconds. Now you got the value of 0.29 and you can use equivalent static method for finding the lateral force for this structure. When you are designing RC frame, what do you mean by RC frame? If you are constructing your building with only column and beam, then you can use RC moment resting frame, and when you are using column and beam with concrete, and if you are using steel member for supporting elements, then you can use this formula, and if you are purely building steel moment resting frame, you can use this formula. So, before doing an analysis, when shall I use equivalent static method or response spectrum method? The code gives the phenomena here. Also, when you are designing your building by RC structural wall, that is, if you are including the masonry infills, you have to use 0.075 h power 0.75 divided by root of AW. So, what is this AW? You can find this is the total effective area of walls. W stands for wall and A stands for area. Effective area of wall can be found out by using this formula, and L is called length of wall and D is base dimension If you know that L, D and effective cross section area, you can multiply and find the TA. If the TA is lesser than 0.4 second, you can use equivalent static method. All the other building which is not covered here, you can use 0.09h root of D. Now, design acceleration spectrum. Okay, how to find AH manually is given here. Let us come to our problem. So, this is your building in 3 dimension, and here you are having in 2 dimension, which is being modeled by using this Etabs. Let us start from load pattern. Now you have to introduce 2 loads. What are they? Earthquake load, earthquake in X direction. The type of load will be seismic, and the code what we should take is IS 1893 2016. Add new loading. Now, in Y direction, take the same phenomena, that is seismic, and auto load as the same, and you can add new load. We have added 2 new loads, that is earthquake at X and earthquake at Y. You have to modify the load. Now modify lateral load. Now what we are considering is, so this is X axis and this is Y axis. So when earthquake hit the building at X axis, when earthquake hit the building in Y axis, and how it deforms, how it behaves. Let us analyze this. If the earthquake is crossing in X direction, so let us use these coefficients. Now direction of eccentricity, we can take only X direction. The Y direction we can remove this. Only X direction is considered, and X direction plus eccentricity, X direction minus eccentricity. Now if the earthquake is striking the building, we cannot assume that the earthquake hits in the centroid of the building. So for an object you will be having a centroid. So for the first floor you will be having one centroid, and second floor you will be having the centroid, and the center of mass. The mass center will be located at different points. If the earthquake is striking this building, what happens? It strikes the center of mass, and it does not act at the center of mass. The earthquake might act at some eccentricity for these 2 structures. So that we have to use at least 0.05 of eccentricity. So when we are considering earthquake at X, so let us modify this here. Here we are removing rest of the things. Y directions we will be removing, and only X directions will be considered. In X direction we will be having minus eccentricity and plus eccentricity. Okay, what do you mean by that is, if you are having the mass centroid here, the earthquake might occur at positive side or at negative side. So both the sides it can occur, at least 0.05 of eccentricity. If you can override, if you need any additional eccentricity, you can provide here. Okay. Now story range, that is from bottom story to top. So this is our bottom story. To the top story we need to find, that is top story is story 2. This is basement, first floor, and this is second floor. So we need earthquake analysis to be done in these 3 areas. Okay. Now let us understand what do you mean by seismic coefficient, seismic zone factor Z. Now this is what we are finding. We have different types of seismic zones. So when you are calculating manually, you have to find Z. What do you mean by Z is, zone, seismic zone factor, which is given in table 3. I is known as importance factor, which is given in separate table. R is known as response reduction factor, which is given, and SA by G is acceleration coefficient for different types of soil. So this is parameter of soil, this is zone, and what are the type of building, what is your importance of building. If it is a critical lifeline structure, if you are building any hospital, if you are constructing any fire station or any important buildings which are telecommunication, these kind of buildings are critical when you are saving some life. During any earthquake, if the telecommunication center is being collapsed, what happens? The communication cannot be done. Finally, we cannot rescue the members who are being affected by earthquake. So that is why these structures are called lifeline structures. And 1.2, which has to be taken for business continuity structures. When you are constructing a residential structure, it is different. If you are constructing any shopping malls, or it might be MNC construction, that is multinational company and trading center, these kind of structures can be taken as 1.2 and rest can be taken as 1. Okay, what do you mean by response reduction factor? Here is, let us discuss in the separate slide. Okay, now how to differentiate soil? So here I have said that SA by G is taken as design acceleration coefficient for different soil type. What are the types of soil? Is when the soil is having a rock or hard soil, it is been classified as type A. If the soil is medium or stiff soil, it is taken as type B. If the soil is soft soil, it is type C, and if it is unstable and collapsible, or it might be liquefiable, it is taken as type D. Okay, generally it is understood that if your soil is very strong, it is type A, if it is medium, type B, like that. Okay, how technically we can classify here is, there is a test which we can do, standard penetration test, that is SPT. If you are doing the test, you will be getting n values, that is n as a constant. The n values have to be above 30. During a standard penetration test, if you are getting n value above 30, it is to be taken as rock or hard soil. So when you want to construct a building, what you have to do is, first the designer needs soil investigation report. So without soil investigation report, we cannot start designing. So before a client meet a structural engineer, he should have a plan, approved plan, and the soil test report in order to proceed the design. So this is the conventional way. You do not skip this procedure. Then medium or soft soil. If you want to classify this, when doing the SPT test, you will be getting value around 10 to 30. So above 30 is called rock soil. When it is coming under 10 to 30, it is called a medium or stiff soil. What do you mean by soft soil is, you will be having much lesser value than 10. If you are having less than that, you can classify it as the soft soil. Unsuitable collapsible liquefiable soils, which has to be tested, and it requires site specific study or special treatment is required. If you are having lesser than these values, that is lesser than this 10, you should first treat the soil. You should make the soil stable in order to construct. If you are having more than 10, you don't need to make any soil treatment. But if it is not above 10, you have to make the soil treatment first, make the soil stable, then make the test, that is SPT test, confirm that it is over 10. Short table, which easily identifies that under which zone. If you are in Bangalore, you will be having zone 2. Okay, what should be your depth of foundation? Depth of foundation is less than 5 meter, then SPT n values 10 is enough. If you are constructing in zone 2 and above 10 meter of depth below the ground level, then your N value should be 20. If you are constructing in zone 3, zone 4 and zone 5, it can be Himachal Pradesh area, Madhya Pradesh, Andhra Pradesh, and these areas you will be having different zones. Under these zones, you have to check that if you are constructing below the ground level for less than 5 meter, then your N value should be 15. If you are constructing more than 10 meter below the ground, your N value should be 25. Z is called seismic zone factor. Why we are discussing here? Here you have Z called seismic zone factor. You have to select it as 0.1, 0.16, 0.24 or 0.36. Now, how to find that? You have to check the code book. So, when you are checking the code book, you know that table 3 is seismic zone factor Z. And when you are taking the seismic zone factor, you have to classify Z2 is 0.1, zone 3 is 0.16, 0.24 and 0.36. So, you have different values. So, the same values is applicable here. How it is written exactly, whatever your code has been considered. Why? Because when you are, let me give an example. When you are selecting here, you are selecting IS 1893. If you are selecting different code, these options might not come. When you are selecting IS 1893, the code book suggests that you should take the 4 zones. Okay. Now, let me assume this building is constructed in Bangalore. You can see that this is the India map. All the areas which are covered by zone 2, 3, 4 or 5. So, the blue lines are called zone 2. You can see the Bangalore is situated here, and the blue lines are called safest zone. If you are constructing building under these zones are much safer, that is zone 2. Now, zone 3 is the coastal area in the peninsular part. You can observe here, these are all called, so this is the mid portion of our country, and in these areas if you are constructing, you can take zone 3, zone 4 and zone 5. You can take this as zone 4. Why these portions are known as zone 5 is you are having tectonic plate. These portions you are having tectonic plates, hence it is taken as zone 5, and several earthquakes have been occurred in India only in these areas. They are major earthquakes. If you are building in zone 5, you have to make sure that your building is much more stable for earthquake. Now you can see that this area, that is Andaman and Nicobar, Lakshadweep, these areas are being highly affected by earthquake force. So that is why it is indicated in zone 5. Okay. By this map you cannot understand directly. So you have to look into here. Annex E. So what is the purpose of Annex E is for all the towns. The zone is given and also the factor constant is given. If you are in Bangalore, you can use 0.10. If you are in Agra, 0.16, and these areas, those who are placed in Bangladesh, zone 5, these areas are around tectonic plates. When you are in Nepal, Bangladesh, Bhutan, these are seismic prone zones. Myanmar, why? Because the tectonic plates merges this area. So, your structure, wherever you are building as a civil engineer, you should be responsible, and whenever you build your structure, make sure that it is earthquake resistant only. Without seismic consideration, you do not provide your consultancy. We can find for all the areas. Calicut, you can see that it is in zone 3. Like that, you can see and search for your zone, and you have to take appropriately. But as of now, I will be taking Bangalore, and for Bangalore, it is 0.1. So I will be taking here as 0.1. Now, what is the site type? Either you are taking 1, 2 or 3. So these 3 are your types. So let me give you an explanation here. These are the 3 types, 1, 2 and 3, A, B, C. These 3 are the types. Now the Bangalore majorly it has a rock or hard soil. So I am assuming that It is rock and hard soil. You can see the classification here 1, 2 or 3. What do you mean by 1? Rock or hard soil, which is having N above 30. So I am assuming that which is having N is above 30, and let me assume it as 1. Now importance factor. What do you mean by importance factor? Yes, table 8. You can find this in IS 1893. In table 8 you have different types. The importance structure, which are example hospital building, telephone exchange, television station, radio station, bus station, metro rail buildings, railway station. These are all called importance factors. In no case they can fail. Whatever might be the earthquake, these structures should not fail. If you are constructing a food storage building, fuel station that are petrol bunks, which comes under importance factor 1.5. Power station, it might be thermal power station, and nuclear power station is also coming under this importance structure. Even though nuclear power structure have different code book, it is suggesting here that if you are constructing any power station, it might be wind or it might be hydraulic power station, thermal, it should be considered as 1.5. Large community hall building, example cinema hall, shopping mall, assembly halls. All the things should be considered as importance factor 1.5. Now, residential or commercial building, other than that, which is 1.2. Now you are constructing a residential building. You should take importance factor as 1.2. Rest of the building can be taken as 1. Now let us take it as importance factor as 1.2. Now these three things are very much important. Okay. Now let us use the same phenomena here, modify load. Since this is earthquake in y direction, let us use only y direction here. And our zone is 0.1, soil type is 1, importance factor is 1.2. The same value which we have used in x-axis we are going to use here. Then press OK. Now press OK here. Now we have provided load patterns. Let us go to load cases. Now we are considering dead load, live load, super dead load. Note that all the load cases are linear static. We are only doing the static analysis. Even though wind and earthquake are dynamic, equivalent static method is a static type of analysis. You will be not considering the load which are time variant. The load is not varying due to time. So this is the understanding here. Now we have to make all the floor as diaphragm. Now let me take here base. Let us take the story 1, apply. I will be having the first story. Let me select all the floors. Now 7 shells are being selected, and if I am selecting all the floors, I have to assign diaphragm. Here in assign you have diaphragm here. So you have to go for this option. D1 is called diaphragm. There are two types of diaphragm here, which are rigid and semi-rigid. So as of now we will be considering the diaphragm as rigid only. Okay, and we have defined the diaphragm. Let us apply. Yes, currently what happened, all the floor mass is been assumed that it is a single component. Now you have to apply diaphragm for second floor also. Select the 2 floor and apply, press OK. Now you have assigned two number of diaphragms. You can see here the first floor diaphragm is, and the center of the mass is located at D1. Why it is converged at a single point is all the loads which are acting in a floor, even the dead load, live load, floor finishes, masonry walls, everything which is been acting in the floor only. The floor load is being taken as a single point. All the masses are being considered and it is being assumed to act at a single point. So this is called mass center. So you are having mass center from, so let us take this as 0, 0. From here you have to measure the x distance and the y distance. So you can locate the center point here. You can easily locate this. Like the same way you have to measure from here to this point x axis and the y axis. So if you are taking this, you will be getting center of mass. So earthquake force will be applied plus 5% of this, minus 5% of this, and exactly the earthquake load will be acting at this center of mass. Like the same way, the earthquake force will be acting exactly at the center, plus 0.05% and minus 0.05%, and it will show the result. Okay, let us define load cases and load combinations. Let us add design default combination for concrete frames, convert, and OK. You can see that number of load combinations it has been made. Okay, you can check here that what is U1, which is 1.5 times dead load and 1.5 times live load, and what is UD. 2 is 1.5 times dead, 1.5 times live, and 1.5 times super dead load. The same way, you can rename this. If you want to rename, you can rename this. And here you can see third load is wind load. You can observe here that the third load, which only consists of dead load, live load, and if I am clicking here, double click, UD3 concrete is dead load, live load, super dead load, and wind load in x direction only, which is covering 1.2. Let us press OK. And U4 is, you can see wind is acting in negative direction of x. And let us press OK. And when you are going to this component, dead load, live load, super dead load, and wind is acting in y direction. For simplifying this, dead load plus live load plus wind in y direction. You can modify this. Now it has been modified. So for understanding, so you can parallelly check the code book. So whatever in IS 1893 which is given, let me explain here. Now, what is response reduction factor R? Okay, what do you mean by response reduction factor is, if you are constructing moment resisting frame system, you can take RC building with ordinary moment resisting frame. This is what we are doing now. We can take it as 3. When RC building with special moment resisting frame, if you are providing joints, Indian standard 13920, which is having a separate code book on how to make special moment resisting frame. If you are following that, you can use RS5. So rest of the things which in future webinars or in future classes, let us discuss that. When you are doing for flat slab, dual system, structural wall, braced system, you might use the different case for your response reduction factor. But as of now, moment frame system in RC building which is having moment resisting frame, you can use R as 3. Now let us once check that have we used R as 3. So we have to implement in define load pattern in x direction, in modify, yes, response reduction factor, we have to take it as 3. also in y direction. Response reduction factor should be 3. Now, okay. Here, this is what we are doing now. The code suggests that load combinations and increase in permissible stresses. It is saying that dead load, whatever we have considered as dead load, super dead load, both are dead load. You should multiply 1.2 times dead load, live load, earthquake load in x direction plus 0.3 times earthquake load in y direction. That the simple concept is 1.2 times and both are 1.5 times and 0.9 times dead load and 1.5 times earthquake load. So this is the same way it automatically calculates here. Define. Now in load combinations you can see here that 0.9 times dead load and 1.5 times wind load. 0.9 times dead load and 1.5 times wind load. So this is what. Note that in automatic load combination, either you will be having wind load or you will be having earthquake load. You can see that. From here we have the earthquake load. Dead load plus live load plus super dead load minus earthquake load in x direction, which is having a multiplication factor of 1.2. So how many calculations are being saved now? If you are doing it manually, this much of calculations and this much of iterations you have to do it. But in earthquake resistant design, in the Etabs or by using the software, these are very much easy. Now you can start analyzing the structure. Let us check the model once. The model has been checked, no warning message is generated, and it is good to do the analysis now. Now set load cases to run. What are the load cases it will be doing is model analysis. This is model eigenvalue. You have to do a model eigenvalue analysis, and what are the loads you have given? Dead load, live load, super dead load, wind load and earthquake in x and y direction. All the calculations will be done now. Let us run now. Now the analysis is going on. This is the status bar. You can check here. Our analysis is over. First let us understand the deflection. If we are providing dead load, now in load case you only have dead load. If you are only having dead load, if you apply, you can see that the structure is going to deflect up and down. Why? Because the dead load is acting downward, which is under gravity. You can see that the maximum deflection due to dead load is 0.8 mm. So the deflection will be up and down. Yes, you can observe here. Let us look into wind load in x direction. Now we have applied the wind load in x direction. And let us start animation now. Note here that the current deflection is in lateral mode. We have applied this as x direction and we have applied the x. The structure is vibrating in this direction, that is x direction alone. We have applied wind in y direction. Let us press apply here. We have applied y in this direction. Now if you start animation, structure will apply the wind load in y direction and it gives the deflection. Now you can check that the deflection is occurring only in this mode, in y direction only. Okay, now let us check for earthquake in x direction. Let us apply. Now this is our axis. You can note here that this is x-axis. The structure is going to deflect in this manner. Start animation. Now if you press y direction, it will deflect in the opposite way. Now let us start animation. Yes. Right now you got an idea about how we have applied the load and how the structure is getting deflected. And let us understand the reactions. Let us go to reaction. Let us understand the dead load reaction. Apply. Stop animation. If you want additional windows, you can use it here. Add new window. You will be having a new window here. You can see that two windows are being opened now. Whatever window is not required, you can close that. Let us go to base and apply. Now these are your reactions. Yes, let us understand from here. If you are providing dead load, you are having a load of 195.49 as Fy. That is 19 ton of load is being transferred to this column and 16 ton of load is being transferred. 155 is 15 ton, 11.5 ton and 114 is 11.4 ton of load. So this much of load is being transferred to this column. You can see this column is carrying less number of load, which is only 9.3 tons and this is 4.3 tons since this is a staircase column. And if you apply the live load, you can see that this has been varying. But whatever might be the load case, you can observe here that this is our critical column. It is having higher load. Fy is 44. Rest of the area you can see less load only. And if you apply earthquake load, now we are interested in knowing earthquake load. You can see that when you apply earthquake load, earthquake is a lateral force, not a vertical force. Hence you can see that in f of x direction, you have an earthquake force of 1.75 kilonewton of force which is acting horizontally. And here is the maximum 2.27 kilonewton of force which is acting in x direction. And in y direction you can see Fy is 0.08, 0.06, all are in terms of 0. Since you have applied earthquake force in x direction, you have maximum force in x. If you want to know in y direction, you can see that now f of x became 0.0. All the areas you don't have x-axis force, which are very less. When the earthquake is acting in this direction, you will be having y direction of force, minus 1.8, minus 1.5, minus 0.46, 6.1976. Rest of the forces are very less. So earthquake is predominantly a horizontal force. We have found out the horizontal force. Now you can also check the load combination. Which load is the highest? You can check that. This is your highest load. Dead load, earthquake load into 1.5. So you can see that f of x, f of z is 557, and you can see f of y as 3.3 and f of x as 2.69. So these are the different load combinations. For each and every load combination, you can check this. Note here that 488. Previously you got 522. This is our yes. Dead load, super dead load, wind load in x direction, which is 1.5, which is having a maximum horizontal force and vertical force. You can see moment. Okay, this is the way to get analysis. If you go in detail, you can check lots and lots of things, but since this is basic understanding, I have taken a small building which is having a 2 BHK house. So right now we are looking into different aspects. I want you to touch the different aspects. In detail you can look into this. Now you can check moment, earthquake. Due to earthquake, what are all the moments? You can check here and apply. Where you can find the maximum bending moment. You can check the bending moment in x direction. If you need in y direction, you can check it. In y direction, you can see the bending moment is in y axis. This is y axis. You can see all the bending occurring in y axis. And due to wind, also shear force, you can check it here. These are the shear force. Earthquake loading, apply. Also, you can check the mode shape. This is your first mode. If you need to know the mode shape and fundamental modes, you can check it from here. In a dynamic analysis, mode shape is very much required. Note here, when we are applying the model analysis, you can check here the period has become 0.28, which we have analyzed by using a formula earlier. The time period is nearly matching 0.2. So the structure is having 0.2 of fundamental natural frequency for mode 1. Since you are having different modes, let us check the next mode. This is mode 2. Both the modes are horizontal and one mode is moment. Since you have two loads, this is the first floor, x, y and a rotation. You can take it x, y and rotation. So you can take 6 number of modes, which we have taken here, 2, 3, 4, 5 and 6. So these are the different modes. For each and every mode, you can check the time period here. For mode 1, the time period is 0.28. For mode 2, time period is 0.188. For mode 3 is 0.154. This is the way to get the mode shape. Yes. As of now, we have analyzed the building by using equivalent static load.